That probably did the trick. I had my mic turned off. Let me know if you can hear me now. Pretty sure you should be able to, though. Very high quality. Nice. That's what I'm looking for. Okay, let me just get some worksheets up so I can steal some questions. And then we'll jump right into it. Okay, we have 6 people. It'd be nice if we had, 8 or 9 people. So we'll just we'll keep waiting for people to show up. If you know someone who logged in earlier and didn't see me online because of the technical difficulties, maybe let them know that that we're back. Okay, this is what we're going to talk about today. We're going to talk about adding and subtracting. So, yeah, we got 7 people here now, so we're gonna just get started. Oh, I should just see if anyone is on Discord. Doesn't seem like very many people in this class are interested in Discord, which is fine. But I should just double check that no one is waiting for me on Discord. Looks like one person is, but I can see that they're also on YouTube. So I'll just I'll leave it at that. I'll leave the I'll join into the voice channel. So if anyone wants to chime in and ask a question with their voice, they're welcome to. Anyway, okay, let's talk about adding and subtracting radicals. So this has a lot to do with something that you would have done a little while ago, like probably like in grade 9, which is a lot like adding and subtracting like terms in an algebraic expression. So adding and subtracting radicals is a lot like adding and subtracting like terms. Okay, so for example, consider something like this, where we are adding 3x plus 6x, right? These are like terms, right? So this would give us 9x. Similarly, we could do a different one. We could have maybe 9x minus 3y plus 6x plus 15y. Now, we have some terms that are like terms and some terms that are not like terms, but we kind of just have to pick and choose which one is which and sort of match them together. So in this case, we would get, well, we've got 9x and 6x, that would be 15x, and we've got negative 3y and 15y, which would be 12y. So we're going to be doing something very similar with our radicals. The only thing that's different is that we're not actually using x's and y's. We'll be using different radicals. So let's take a look at a few examples. So let's try this example here. So let's add this. So I've got the square root of 27, plus the square root of 12, minus the square root of 8. Okay. Now, if you wanted to, you could punch this into your calculator and get some kind of decimal approximation. But something that we'll probably see a little bit later is that these are all irrational numbers. All of these are irrational numbers. So the way radicals work is that either you get the square root of a perfect square, which is going to be some kind of rational number. So you could have like the square root of 16. That's going to give you 4, right? But if it's not a perfect square, like if it was the square root of 15, all of a sudden this is an irrational number, which gives us a decimal expansion that has no pattern and no repetition, and the decimals keep going on forever. So even if you did want to punch this into your calculator, you would just be eyeballing it. There wouldn't be any sort of precision in that. So what we're going for here is an exact value, and we want to simplify that exact value as much as we can. So the way we'll do that is by simplifying each one of these radicals. So effectively factoring out the largest perfect square that we can. So in this case, I think I can factor out a 9, because 9 is a factor of 27, and 9 is also a perfect square. So let's factor out a 9, so that would give me 3 times the square root of 3, right? Because 27 divided by 9 is 3, and the square root of 9 is 3, so that's why there's 2 3's there. Let's see here. This one, I think I can factor out a 4, right? Because 4 is a perfect square, and 4 is a factor of 12. When I do that, when I take out the square root of 4, I get a 2, and what's left over when I factor out a 4 from 12 is 3. Okay, getting somewhere. Now, when I simplify the square root of 8, well, I'm going to factor out a 4, and the square root of 4 is 2, and what's left over is 2. So I've got 3 root 3 plus 2 root 3 minus 2 root 2. Perfect. Now I can see that this is the same as this. So these are like terms. These are like terms. I can add these together. So what I'm going to get is, and I should be writing equal signs here, this is equal to, well, 3 plus 2 is 5. So I've got 5 times the square root of 3. And what's left over is just this 2 root 2. And I can't add that to the other radical because they're not like terms. They're not like radicals. So we have to be careful when we're adding these, because we can only add them if they have exactly the same radicand. Okay? All right, let's see. Oh, and I think was there someone who asked a question yesterday? I think someone asked a question on Instagram. So let me just quickly run through my Instagram and see what that person asked. Oh no, that was for a different class, I think. If you have a question about the homework from yesterday, just throw that question into the chat really quick, and I'll address the question now. But if I recall correctly, I don't think anyone actually had a question. Not for this class. I had a few questions from other classes, but anyway, let's carry on. Let's do another one. Let's try simplifying. So let's simplify this one. Let's do, this is a good one. 4 times the cube root of 16 plus 3 times the cube root of 54. Okay, so here is this question. Okay, so we are looking for perfect cubes, and it might be helpful just to write the first few perfect cubes. So let's write this down. So 1 cubed, that's just 1, obviously. 2 cubed is 8, and you can see how quickly the cubes grow. The second one is already 8. 3 cubed is 27, And I think that's all we really need. Let's just have this on the side here. So let's see which ones we can factor out. I'm going to factor out an 8 from here. And just because now that these are cubes, I want to just write this one extra step just so that everyone is aware of what I'm doing. So this is equal to 4 times the cube root of 8 times the cube root of 2, right? Because 8 times 2 is 16, and the way that these radicals multiply against each other, the product of two radicals is the radical of the product. So that works out nicely. And same with this one with 54. I've got 3 times, well, 27 is a factor of 54, so let's write the cube root of 27 times the cube root of 2, because 27 times 2 is 54, and this should be a cube root. Okay, so now let's simplify this even more. So this is, well, 4 times 2, right? Because the cube root of 8 is 2, times the cube root of 2, plus 3 times, well, the cube root of 27 is 3, and I'm left with the cube root of 2 left over. Let's clean this up a little bit. So 4 times 2 is 8. So I got 8 times the cube root of 2 plus 9 times the cube root of 2. And these are like radicals. So I've got the cube root of 2 and the cube root of 2. So let's go ahead and combine these. So 8 plus 9 is 17, and I've got 17 times the cube root of 2. So that worked out pretty nicely. I think that one wasn't too bad. Let's try a few with some variables in there for some extra spice. Let's see what we have here. So let's simplify. Yeah, this looks like a good one. We're gonna simplify. Let's simplify this one. Yeah, we're gonna do 5 over 2 times the cube root of 16x to the 4, 16x to the 4, y to the 5, that's my first radical, minus x times y times the cube root of 54 xy squared. Okay, let's try this one. See what we get. Okay. So I've got 5 halves times the cube root of 16x to the 4, y to the 5, minus xy times the cube root of 54xy squared. Okay, cool. So let's start to split this up, and what we'll try to do is we'll try to split this up into a perfect cube and leave everything else and then see what's left over. So I'm going to say that this is 5 halves times the cube root of, well, let's see what the biggest cube that we can pull out of this is. Well, I'm going to say that this is 8, right? Because 8 is a perfect cube and it's a factor of 16, so I won't have any problems with that. 8x cubed, right? Because x cubed is a factor of x to the 4, right? And I'll do y cubed as well. So that's what I'm factoring out. I'm going to give myself a little more room because I'm kind of running out of room here. That's better. And I'll multiply that by whatever is left over, by the cube root, and I'll just give myself a little more room there. Cube root of, well, when I took the 8 away from 16, I was left with 2. When I took the x cubed away from x to the 4, I've just got 1x left. And when I took the y cubed away from y to the 5, I got y squared left. So that's what's left over for that one. And I think I'm going to need even a little more room, so bear with me here. Now let's see what's on the right. So I'm going to subtract xy times, and it looks like we've got the same numbers as last time, right? We had 16 and 54, and we're taking the cube root. So hopefully we can remember that 27 is a perfect square, or sorry, a perfect cube. That is a factor of 54. And it doesn't look like I can take out an x or a y, so I'm just going to leave it at that. and I've got the, basically everything left over, which is 2 times xy squared. So there was no perfect cubes in the variables because there weren't enough variables. Oh, look who decided to say hi. I think she misses you. It's been a while. Okay, say hi, Goose. Okay, back to reality. Okay. Oh, is there a question here? No. Okay, let's see here. Sorry, I got distracted a little bit. It's easy to get distracted by Goose. She's a major distractor in this house. Okay, so let's start taking these cube roots. So I've got 5 over 2, right? That part doesn't change. And now I can take the cube root of this. So the cube root of 8 is 2, so I'll write times 2. The cube root of x cubed is x, and the cube root of y cubed is y. And then I'll just write everything over here. This is the part that we can't take the cube root of, so we've got 2xy squared minus xy times, well, the cube root of 27 is 3 times whatever's left over, so I've got 3 times 2xy squared. Let's clean this up a little bit, and if you're really paying attention, you may have noticed that we've got a 2xy squared, and we're taking the cube root of it. So we do these are actually like terms here, or like radicals, if you will. That said, I want to clean it up first. That way, when we add them, it'll be very clear what we're supposed to do. So let's do that. So I've got 5 halves times 2. 5 halves times 2 is just 5, right? 5 over 2 times 2 is 5. And so I've got 5xy times the cube root of 2xy squared minus, and then really all I'm going to do on this one is just move the 3 out to the front. Okay? Because it's customary to put the coefficient in front of variables, right? So we're going to put the 3, and then we'll write 3xy times the cube root of 2xy squared. Okay, that looks good. And it looks like I've got just enough room to finish this off. So I've got 5xy. And I should also point out, too, that these are like terms too, the x and the y. So I don't even have to worry about, you know, adding and subtracting variables. So I've got 5xy minus 3xy, which is just 2xy. 2xy times the cube root of 2xy squared. And that worked out pretty nicely, actually. I think that was a nice example. Let's see here. So I'd like us to finish up with radicals by the end of the week, and this is actually a short week. I know that there's a lot going on in our lives, but so it may have been easy to forget that tomorrow is actually or not tomorrow, Friday is Good Friday. So that means that we have a 4-day week, which is super awesome. So I'd like us to try to finish up with radicals. So what I'm going to try to do is I'm going to try to get through this whole section. Oh, do the x, y's not cancel out? Good question. I'm gonna get to that in 1 second. I'm just gonna finish this thought, but that's a very good question. So yeah, really all we have to do left for radicals is we're going to do some multiplying and dividing, and I'd like us to learn about rationalizing the denominator. So let's see here. Oh, and then we have radical equations. You know, we might not actually be able to finish this week. I thought maybe we could finish it this week, but I think that might be a little ambitious. So yeah, I think that we are going to have to go bleed into next week just a little bit. Okay, anyway, back to this question. So in the chat, somebody just asked, do the x and y's cancel? So let's consider this. So So I've got 5xy cubed minus, 2xy squared minus 3xy cubed times 2xy squared. Okay, so let's think of this whole thing as like let's consider it as its own variable. Let's suppose z, this new variable that I have. Let's say that z is equal to xy cubed. Oh no, sorry, not xy cubed. Xy times the cube root of 2xy squared. Let's just say that was our variable, and that would mean that this, everything in pink here, that's what z is. So then we would have 5z minus 3z, and that's clearly 2z, right? That's 2z. So thinking of it like that, no, they wouldn't cancel out, because z, now I would put z back into the equation. So this would be 2 times xy times the cube root of 2xy squared, right? So that's one way of thinking about it. Another way to think about it is if we were to write this whole equation out again. I'm just going to copy and paste it because I'm lazy. So copy and paste. Okay, so another way to think about it is to say, okay, well, I've got this guy right here. So that's my that is my radical. So you don't even have to think about it in terms of like terms. You could just think about it in terms of the like radical. So you could say, okay, well, I've got one and the other. I'm going to subtract one from the other. I'm going to have, well, I've got 5xy minus 3xy, and that's what I'm left with, the 5xy minus 3xy, and all of that multiplied by the cube root of 2xy squared. Okay, and well, if I have 5xy minus 3xy, well, that would be 2xy. And now we would just be thinking of that in terms of like terms. So we'd have 2xy times the cube root of 2xy squared. Okay, so I hope that answers your question. I think I kind of went a little overboard with the answer, but there's lots of different ways of thinking about this. Okay, so there's a couple more things I'd like to talk about, and then, yeah, I think if all goes well and my timing is accurate, and I'm a little annoyed that I had these technical difficulties this morning, but that's just the nature of distance learning, I suppose. What I'd like us to do right now is talk about multiplying and dividing radicals. So let me just pull up some examples. Okay, so we've done simplifying radicals. That's good. That's kind of what we started out with. We've done adding and subtracting radicals. Now I want us to do multiplying and dividing radicals. Now I've always found that multiplying and dividing radicals are actually much more straightforward than adding and subtracting radicals. Multiplying and dividing, it kind of just works out in a much cleaner way. There's typically less work involved, but we'll see. Some of the questions will actually get more challenging, but the concept is, I think, a little bit easier to swallow than adding and subtracting. So let's go ahead and try this question out. So let's try to multiply. So we're going to multiply. Let's multiply 2 times the square root of 6 times 5 times the square root of 3. Okay? So one thing to keep in mind is that 2 root 6, that means 2 times root 6, and 5 root 3 means 5 times root 3. So what this really means is 2 times 5. 2 times 5. I'm really just sort of rearranging the terms. It means 2 times 5 times root 6 times root 3. So you can just rearrange these terms in whatever way you like. And then 2 times 5, that's 10. And now I've got root 6 times root 3 is root 18. And now we can simplify this a little bit, which means that this is 10 times, well, I can factor out a 9, right? 9 is a perfect square. That's a factor of 18. So when I do that, I'm left with 3, because the square root of 9 is 3, and I'm left with 2 left over, and that's 30 times the square root of 2. So that's not bad. I don't think that's too bad. Yeah, that one wasn't too bad. Let's try a couple more. Okay, let's do one that needs the distributive property. I think that this is a good question. And I think we looked at something similar to this yesterday, didn't we? I think we did. Let me just scroll back to what we did yesterday. I mean, we did some stuff with the distributive property, but it was like the exponent distributive. Yeah, no, we did do something like this. So let's try something like this again. Yeah, okay, so I'll pretty much do this same question again, but it'll be a little bit different. Yeah, let's do this one, and then I'll do one that's a little more challenging, because we've already sort of seen something that looks like this. Okay, so let's do 2 times root 3, so we'll do 2 root 3, 2 root 3 minus 3 root 2, 3 root 2, and this is getting a little bit thick for me. There we go. Okay, 3 root 2 times 2 root 3 again, 2 root 3, plus root 2. Okay, so I've got, and yeah, okay, so that is the way it is. Okay, so the way I like to do these is I think of every single term in here having to multiply every single term in here. So maybe what we can do is, let's do it like a little color coding thing. And so yeah, I'll get 4 different colors. So I've got, this is going to be my pink. This is going to be, let's do green. So right over here, this is my green. This is going to be yellow. And let's do one more color. Let's do, I've already got purple. How about orange? So this is my orange, okay? So the way this is going to work is all of these guys on the left here, and I'll go back to blue as kind of the standard color. So all of these guys on the left have to multiply all of these guys on the right. That's just how the distributive property works, okay? So when I do this, I'm going to get, well, let's do purple and yellow first. So we'll do purple and yellow first. So this pair, that's going to give me, well, 2 root 3 times 2 root 3, okay? Next up, I'm going to have purple and orange. So we'll have purple and orange, so that's good. And what I'm left with there, so purple and orange is going to be, well, plus 2 root 3, and orange is root 2. Okay, so that's good. Now I'm going to have green, because I'm going to multiply all of these by something green. And let me get the yellow out. Okay, so now I've got green times yellow. Okay, so green times yellow is going to be, got to go back to blue. I only have 3 colors at once that I can choose from, which is kind of annoying, but that's how it goes. And don't forget, this is there's a minus sign here. This is a subtraction that we have to worry about. So all of these are going to be minus. So I've got minus 3 root 2, and I'm going to multiply that by 2 root 3. And finally, I've got, what is it, green and orange. So green and orange all together. I'm going to get, well, don't forget, it's also minus. So I've got minus 3 root 2 times root 2. Okay, so that looks good. Now what I'm going to do is I'm going to just simplify everything, and then maybe I'll get some like terms, maybe not, we'll see. So this first one here, the what was it, the purple yellow? So this purple yellow one, let's simplify that. I've got, well, 2 times 2 is 4. So I've got 4 times the square root of 9, and I'm gonna clean that up later. I know that that's 3, but I'm gonna leave it for now. Then I'm gonna have, well, 2 times the square root of 3 times the square root of 2. That's gonna be 2 root 6. Okay, next one is minus 6 root 6. The one after that is minus 3 root 4. Okay, that looks pretty good. So again, I'll clean this up, and I should be writing equal signs at every stage. So I've got 4 times the square root of 9. That is 4 times 3. Actually, I'm just going to write that as 12. Okay, so that's 12. Plus, well, I've got 2 root 6 minus 6 root 6. That is going to be minus, so I should actually write a minus sign here. That's going to be minus 4 root 6. And then this last one here, I've got minus 3 root 4. That's going to be 3 times 2, which is 6. So I'm going to have minus 6. And finally, I'll clean it up one more time. This is equal to, well, 12 minus 6 is 6. I've got 6 minus 4 root 6. Awesome. That one wasn't too bad. Okay, let's do, you know what, I'm gonna leave that one alone. Actually, you know what, let's do this one more, and then we'll call it a day, and I'll post some homework on the website shortly. That should be a good reflection of what we did today. And then tomorrow what we're gonna do is we're gonna do something called rationalizing the denominator, which is actually a pretty big topic. So yeah, that's what we're gonna be doing today, or tomorrow rather. Okay, so okay, let's see here. Yeah, you know what? I think that you could just do that one on. I'm just trying to find a good example for you guys. That's what I'm doing here. Okay, let's do this one here. Yeah, this is a good question to do. So okay, let's try this one here. So we're gonna multiply square root of x cubed with the cube root of x. And here we're saying that x is greater than or equal to 0. The only reason we're saying that is because if x was negative, well, then then x cubed here, x cubed would be negative, and then we'd be taking the square root of a negative thing. So that's why we're saying that x has to be positive here. Okay, so let's multiply this. Now, this is going to be a little bit tricky because we have we've got an issue, right? This is a square root, and this is a cube root. So what we're gonna do is we're gonna turn these into fractional exponents. Okay. So remember that if I have the nth root of a to the m, that's equal to a to the power of m over n, right? So we're gonna convert these into fractional exponents, and then these are actually gonna be quite straightforward to multiply. So this is going to be x to the power of 3 over 2, and we're going to multiply that with x to the power of 1/3. Okay. Now, because we're multiplying two variables, or two powers rather, these are two powers, and they have the same base, that base is x, all we have to do is add their exponents, right? Another thing that we learned yesterday was that a to the power of b times a to the power of c is equal to a to the power of b plus c. So all we're going to do is just add these exponents and we'll be done. So this is equal to x to the 3 halves plus 1/3. Well, let's see what that's equal to. Well, I'm going to do that on the side here. So, oops, not 1. 3 over 2 plus 1/3. Well, I have to change these denominators. So this is, I'm going to multiply this by 3 and this by 2 because the least common denominator is 6. So that gives me, what is that, 9/6 plus 2/6. So that would give me 11/6. So this is going to be x to the 11 over 6. Or if we wanted to write that as a radical, we would say that this is the 6th root of x to the 11. And I think I may have made a mistake here. Or, you know what? We're actually not quite finished here yet because this isn't simplified, right? We have a 6th power that we haven't factored out. So keep in mind this is equal to the 6th power, or the 6th root of x to the 6 times x to the 5. And that's equal to, x times the 6th root of x to the 5. And that's perfectly simplified. So that's the way that we can think about multiplying radicals that have a different index, is just convert it into a fractional exponent, and then all the work is just adding fractions. So that's kind of what I like to prefer to do. So yeah, we're gonna end it there. I'm gonna post some homework on the website very shortly. Hopefully by by noon, so within the hour, I'll post some homework on the website. Yeah, so that just leaves us, I think, 1 or 2 more sections to do in this chapter that I'm following along, and then yeah, maybe we can start thinking about another assignment. So I think that I've finally got everyone's assignment from last time, so I'm gonna start grading them and returning them. So yeah, stay tuned for that. Yeah, if you have any questions, don't hesitate to reach out, and I'll talk to you guys tomorrow. So take care.